Good morning, everybody. I hope everybody is well. Today, again, we will continue with inductance and circuits contain inductors. During the last lecture, we have seen mutual inductance, and we have also seen self-inductance, an inductor or coil in a circuit. And if there is a changing current, time-varying current within the circuit, then there is a self-induced EMF within the inductor in the circuit. So we have discussed all these things. We have discussed the energy stored in an inductor. So today we will continue with different combinations of circuits which contain inductor. So we will start with the RL circuit. In RL circuit, we have a resistor and also inductor. And in addition to that, we have an EMF source. So here you see a typical RL circuit. Here we have switch 1, here we have switch 2. We will use them to open and close that part of circuit, and that part of circuit later on I will show you. So now let's consider the first condition. We close S1, switch 1, okay? Then what happens? We have current from positive to the negative in the circuit, okay? And we have potential difference across the resistor here. The potential difference across the resistor is given by I times R. And we have also learned that the potential difference across the inductor is given by L times di over dt. So don't forget this one. If the current in the circuit is constant, if it is not changing, then this term is 0, then there is no potential difference across the inductor. But if there is a time varying current, then we have potential difference across the inductor. So here, let's try to apply Kirchhoff's loop rule. I will not go into detail. You know them, okay? They are summarized here. So you can apply rules for the inductor as we have done for the resistors. So now we have EMF here, okay? And we have a resistor here, minus IR. And here we have inductor, minus L di over dt. And the total potential difference is equal to 0 here within that loop, according to the Kirchhoff's loop rule. So now what we have here, I would like to solve the I over dt within that equation. What is the I over dt? If I take it from that expression, I will get this one. EMF over L, inductance minus resistance over inductance times the current in the circuit. So what do you see here? Current is not constant. It is changing by time, okay? For this reason, we have shown the current by using lowercase letter. So let's continue. Look at that equation. This is the current in the circuit changing by time depends on these parameters. Here we have 3 conditions which I show you with different colors. 3 conditions. So let's have a look for the first case. When we close the switch S1, when the time is 0, the current in the circuit is 0, okay? Just we close the circuit, time is 0. So then there is no current at the beginning in the circuit. And since there is no current, the potential difference here is 0, okay? So then this I is 0 here within that equation, then this term is 0 since current is 0 at the beginning, okay? So then the initial rate of change of current, this one, the I over dt initial, just when we close that switch, when the time is 0, okay? This is 0, then we have EMF over L. This is the first case, first condition. Now, let's have a look. As the current increases, so time goes, okay, and then current increases in the circuit. What about this term, second term? Current is increasing, then this second term will increase, right? Then, what about this one? Since here we have minus sign, and if this increases, this will decrease, right? Then the I over dt becomes smaller and smaller. Current will increase, and then this will decrease. This is the second condition. And what about the third one? When the current reaches a final, so this current here reaches to the maximum current in this circuit, which is constant with value of I, and then this di over dt is 0 because there is no change in the current. Now we have a constant current in this circuit. If you have constant current in this circuit, then this is 0. Current does not change by time, okay? So here we have 0, okay, this one, and just put that terms here. Instead of changing current, here we have a constant current, okay? Then take this one to the left side, and if you take current from that expression, we have current given by EMF over resistance. This is the maximum current in that circuit, and it depends on the EMF of the circuit, and it also depends on the resistance of the resistor. Any question here? Okay, then let's try to get a relation between current and time. Okay, I would like to get that relation. So we have learned that the current changes by time. At the beginning, the current is 0, and then it is increasing, and finally it reaches to the maximum value of this one. Okay, now let's try to get a relation between current and time. So what we do, here we have di, here we have dt. Put that to the right side and put the terms with the current to the left side, then we have that expression. So if you integrate both sides, what do you see? This is the integral over current. Current starts from 0, it goes to I, and time starts from 0, it goes to t, certain time. And if you solve that integral, you will get that expression. If you solve that integral, you will get that expression. And if you take current from that equation, finally, we get current in an RL circuit with EMF. What do you see here? That the current in the circuit is equal to EMF over R times 1 minus E over minus R over L times T. So as the time increases, then this term goes down, and then finally the current equals to E over R after certain time. The current reaches to the maximum value, okay? But between the time is 0 and certain time, we have current like this changes by time. And again, from that expression, you can understand that the current increases by time. So now let's have a look the behavior of current as a function of time in that graph. Here we have time and here we have current, and current changes by time like this. This is the maximum current in that circuit, okay? So which is given by E over R. We have already done it. And what we have here, the instantaneous current I first rises rapidly here, okay? Then increases more slowly here in that region and approaches to the final value of this one, okay? Look at this one, time. When the time is equal to L over R, just put L over R here, then this term will be cancelled, and here we will have E over minus 1. E over minus 1 on the right side, okay? If the time is equal to L over R, then we will have current with that term, E over R times 1 minus 1 over E, okay? So it is about 63% of its final value. So look at this one, time, when the time is equal to L over R, the current in the circuit is given by that expression, I times 1 minus 1 over E. So it is increased to that value within that time, okay? So this quantity, L over R, is a measure of how quickly the current builds toward its final value, how the current goes to its final value, okay? So the time is called as time constant for this circuit, denoted by the tau, which is given by that expression. So what do you see here? Time constant here, time constant here. It depends on the inductance and also it depends on the resistance, right? If the inductance is smaller, then you will have smaller time constant. It means that in a short time, you can reach high currents, okay? If we have small inductance here. Look at this equation also. If you have small inductance here, then you can reach high currents, final currents in a very short time. So this is the meaning of that time constant for RL circuit. Do you have any question here? Okay, then let me continue with the energy storage in the inductor. We have already discussed this one during the last lecture. We can store energy in an inductor in the form of magnetic field. So let's discuss the energy. The instantaneous rate at which the source delivers to the circuit is given by EMF times current, okay? And some part of this energy is dissipated in the resistor, which is given by this one, the instantaneous rate at which energy is dissipated, I squared times R, and the rate at which energy is stored in the inductor is given by I times potential difference across the inductor, okay? We have done it during the last lecture. This is the current, this is the potential difference, L times di over dt, potential difference across the inductor, and then we have that expression. So we deliver energy or power to the circuit, to the system, and some part of the power is dissipated in the resistor, and then some part of it stored within the inductor. So this is the energy storage in an inductor. Let's continue with an example. Here we have example 30.6 from the book, and we will analyze an RL circuit. Here we have an RL circuit, a sensitive electronic device of resistance, which is equal to 175 ohm. Here we have a device with the resistance of this one, okay, is to be connected to a source of EMF, this one, and we consider that this EMF has negligible internal resistance, and we have a switch here. The device is designed to operate with a 36 milliamp current, so the maximum current in the circuit will be 36 milliamp, but to avoid damage to the device, the current can rise to no more than 4.9 milliamp in the first 58 microseconds after the switch is closed. So let's consider that at the beginning switch is open and there is no current here. Whenever we close the switch, there will be current here. So in order to prevent that device from very high currents, so current is limited with inductor. Do you remember our discussion during the last lecture? We have said that the inductors are used in the circuits to prevent the system from large increase or large decrease of the current in the circuit, okay? This is the main aim of the inductor in the circuits. So you save the circuit, you save the devices by using inductors in the circuit. So we would like to limit the current with 4.9 milliamp for the first 58 microseconds after the switch is closed. So then an inductor is therefore connected in series with the device, okay? So question, what is the required source of EMF? EMF is asked. What is the required inductance? So you will put an inductor into the circuit, but what about the inductance of that inductor? Then what is the RL time constant, this guy? So it is very easy to solve. So we know that the maximum current is given by EMF over R. We have done it here. Maximum current condition is this one, EMF over R. Then take EMF from that expression. Maximum current is known, 36 milliamp, and resistance of the resistor is already given. Put it there. So EMF is 6.3 volt. We have found it. So what about the second question? What is the required inductance? So look at that expression. This is the current, depends on the time. And here we have L. If you take L from that expression, we can get equation for inductance. Here we have resistance, here we have certain time, here we have current in the certain time, here we have resistance, here we have EMF. So instead of time here, just put 58 microsecond. Instead of current at that time, just put 4.9 milliamp. Then finally, we can calculate inductance as 69 millihenry. And what about the time constant, tau, which is given by L over R? L is given, put it there. R is given, put it there. So time constant is 390 microsecond. Do you have any question? Okay, so what we have done, we have just circuit, we have two switches. First of all, this is open and then we have closed this one. and then we produce a current in that circuit. Some part of the power is dissipated here, but some part of the energy is stored within that inductor. Now, when the current reaches to the maximum current, we open that switch and bypass that EMF and then close that switch. So then there will be current like this. Okay, the EMF will be bypassed. So this was the first condition. We have stored energy in the inductor, and then we will use that energy. Okay, we will open this one, close this one. Now we have new circuit. I think it is clear. So now what will happen? Due to the resistor in the circuit, the energy stored in the inductor will be dissipated, and this is the power provided by the inductor to that circuit now is equal to the power dissipated in the resistor. Okay, so we have this relation. So if you apply again Kirchhoff's loop rule to that circuit, then you can get current as a function of time, as we have done during the first case. So we have applied Kirchhoff's loop rule to calculate the current as a function of time. We can repeat the same steps also for this one, then we can get current as a function of time. So what we have here? We have here I0. Look at that graph. This is the time, this is the current, and this is the I0, the current at the beginning in the circuit whenever you close the switch to. So at the beginning we have maximum current, then the current decreases by time with that expression, okay, because it is the energy is dissipated in the resistor. So we have again time constant here. At that time, current drops from I0 to that value I0 over E. If you put time constant L over R here, this term will be 1, and then it will be I0 over E, because this will be E over minus 1. So then we have this type of behavior of the current. So during the first case, current increases like this and it goes to maximum value and energy stored in the inductor. And then during the decay, we have this type of current as a function of time. It starts from the maximum I0 value and then it goes to 0 by time. Is that expression. Do you have any question here? Then let's see energy in an RL circuit in that example 30.7. So when the current in an RL circuit is decaying like this one, what fraction of the original energy stored in the inductor has been dissipated after 2.3 time constant? So at the beginning, energy is stored here. Whenever we close that switch, the energy will be dissipated here, right? So the question is that after a certain time, what fraction of the initial energy stored in the inductor has been dissipated? So now let's have a look at the energy. We have done it during the last lecture. Energy in the inductor is given by that expression 1/2 L times I square. L is the inductance of the inductor, I is the current in the circuit. So here we have I, we have calculated I during decaying the current. Just put that I here, and then the energy in the inductor as a function of time can be written like this. What do you see here? We have I0 here within that current. If you put this one here, so we will have I0 square here, then if I take this 1/2 L times I0 square, look at this one. This is the original energy, energy stored in the inductor at the beginning, okay? So just put this name here, U0, okay? The original energy. And here we have that term, okay? So what do you see here? Time. Time is given 2.3 time constant. So 2.3 time constant. Time constant is given by L over R, okay? So just instead of time, just put that expression, 3.L over R. L will cancel this L, R will cancel this R, then here we will have U0 times E over minus 2 times 2.3, okay? Then the energy in the inductor is given by that expression 0.01 U0. What is the meaning of that? This is 1% of the energy initially stored in the inductor remains, okay? So 99% has been dissipated in the resistor. So you can see that how fast the energy is dissipated within the resistor. So you can dissipate the energy very fast, and you can also store the energy within the inductor very fast. Do you have any question here? Then let me continue with LC circuit. This was the RL circuit. Now we will continue with LC circuit. And what about the current in that type of circuits? Here we have an inductor, and here we have a capacitor, okay, with initial maximum charge Qm to the positive side, and the same amount of negative charge on the negative plate to in the right side. So we have potential difference in between, maximum potential difference, and here we have electric field in between the plates. So what happens if I close that switch? So this is the question. And what about the energy relation? So now let's start from the beginning. Let's consider that at the beginning, capacitor is empty, and then we connect an EMF or battery to fully charge the capacitor, and then we charge the capacitor to the maximum charge and maximum potential difference, okay? So then the capacitor is fully charged, but this is open, okay? There is no connection in between. The current is 0 because switch is open. And what about the energy? The energy is stored here in electrical field, okay? The total energy is only given by the electrical energy, UE here. We have done it in capacitors. And the energy in the inductor is 0 because there is no current in the system and the inductor is empty, you can say, okay? So now let's close that switch here, and then there will be current from that positively charged plate to the negative side, okay, like this. So we will have a current here, and this current will start from 0 because at the beginning the current was 0, and then current will increase by time, okay, and it will reach to the maximum current value, as we have discussed during the RL circuits. So when the capacitor potential becomes zero, the induced EMF is also zero here. So let me start from that point. At the beginning, we have positive charge here, negative charge here, and there will be current within that circuit, right? So the current will increase, and then the charge on that plate and that plate of the capacitor will decrease. The charge will decrease and current will increase. And during changing of the current, we will have an self-inductance in this system, which is given by minus L times di over dt. Since we have change in the current in the circuit, then we will have a self-inductance, okay? So this is telling this one. But what happens if we reach to the maximum current? When we reach to the maximum current, the I over dt will be zero, and the EMF here will be zero, and the potential difference here will be zero, because here at the beginning we have potential difference, because we have positive charges here, negative charges here. But at the end, the total charge here is zero. Okay, we have nothing on that plate, we have nothing on that plate, because we have used them to produce a current in the circuit, and we stored the energy into the inductor. Okay, at the beginning we have energy stored in the capacitor, but now the whole energy here is stored in inductor in magnetic field. So now let's continue. What will happen? What about the EMF here and direction of the EMF? So this is the direction of the current in this circuit, right? When the current is changing, let's say at the intermediate time, the current is increasing, okay, in that direction. So this is the positive. Current is increasing, right? And here we have negative number, and we will have an EMF opposite to the initial current here, right? Opposite to the initial current, EMF. Don't forget this one. So now step 3. What we have in this step 3? The capacitor is completely discharged in that step, and the all energy is stored within the inductor. Then this energy will be spent to recharge the capacitor again, okay? So due to the direction of the EMF, we will have current in that direction, okay? So the current direction will be like this. Then positive charges will be collected on the right side of the capacitor, and negative charges will be collected on the left side of the capacitor. So look at the beginning. Here we have positive charges, and then we have current, and then we fill the inductor, let's say, okay? And after this one, the current, direction of the current reverses, okay? And then we collect the positive charges to the right side, negative charges to the left side of the capacitor. So we completely spent the energy stored in the inductor, and then the whole energy is stored in the capacitor as an electric field. So now the total energy is only present in the capacitor as an electric field energy. Then the last step, we have filled the capacitor again, okay? Then you may expect current in that direction to store the energy into the inductor. So it will be like this. We will again store energy into the inductor. Then the whole energy stored in the capacitor will be transferred to the inductor as a magnetic field energy. So if you continue, then you will go to the first step again. Okay, let's continue with the total behavior of the system. I have explained each step separately, okay? Now we will have a look at the complete system, what happens to the current and charge in the system as a function of time. So this is an LC circuit. Here we have inductor, here we have capacitor. At the beginning, we completely charged the capacitor by using an EMF, okay? And then we connected that capacitor to the inductor by using a switch here. So then we have produced a current. This current is increasing by time. And finally, the capacitor is fully discharged, and then current reached to the maximum here within the circuit. Then, when the current reaches to its maximum value, it goes back and refills the capacitor again. So, but the direction of the current is opposite compared to the initial case. Now we have positive charges here on the right side. At the beginning, we had negative charges on the right side. So then we fully charge the capacitor again. After that process, the capacitor discharging and then I increasing again in the opposite direction. So this was the mechanism which we have explained in the previous transparencies. So what we have here, we have time and current, and we have behavior of current as a function of time. Look at the first case here. The current is 0 at the beginning because switch is open. Whenever we close the switch, there is a current in the circuit, and this current is increasing. And it reaches to its maximum value here in that condition, and then it goes back, okay? It goes back and decreasing. And in that condition, current reaches to 0. Again, the capacitor is fully charged and there is no current in the circuit. And it is increasing, and then it reaches to its maximum value, and all the energy stored in the inductor. And at that position, again, we have spent that energy to transfer it to the capacitor, and then the current decreases and reaches to 0 in that condition. So it goes back. So the current is behaving like this. This is the behavior of simple harmonic motion. We will go into detail. So look at the charge on the left plate of the capacitor. At the beginning, the capacitor is fully charged, and then we have maximum charge when the time is 0. And when we close the switch, we have current in the circuit, and the charge on the left side of the plate and the right side of the plate, charge decreases. And the charge on the capacitor goes to 0, okay? And then we start to refill the capacitor in opposite direction. And now on the left side, negative charges are collected, and the amount of charges on the left side is increasing. Then we reach the maximum charge on the left side. Then charge again starts to decrease, and we reach 0 charge here when the capacitor is fully discharged. And if you go back to that position, then again the capacitor is fully charged with positive charges. So this is also oscillating, okay? The current is oscillating by time, and charge is also oscillating by time. So this is called as electrical oscillation in LC circuits, electrical oscillation. But what is the important information here is that we have considered that the resistance of that wires and the resistance of the inductor is zero, okay? This is ideal condition, okay? For this reason, there is no energy dissipated due to the resistance of the wires and resistance of the inductor. Do you have any question here with that part? Then I will try to get expression for the current as a function of time. So it is oscillating and I would like to show it. So again, we can apply Kirchhoff's loop rule to the LC circuit here, okay? I will not go into detail, details are given. So here we have potential difference for the inductor and potential difference between the plates of the capacitor. So it is given by minus Q over C, and they are equal to 0 due to the Kirchhoff's loop rule, okay? Here we have I. Instead of I can write dq over dt. So charge changes as a function of time and it produces current in the circuit. So just put this one, and then instead of this one, I can write this one, d square q over dt square. So then if I divide this one and this one by minus L, then I can get this expression. So this term on the left side plus 1 over LC times Q is equal to 0 for the LC circuit. What do you see here? Look at that expression. This leads to an equation with the same form as that for simple harmonic motion, which we have seen in Physics 1 in chapter 14. Then from that equation, we can get equation for charge. So what do you see here? The charge on the capacitor changes by time and it oscillates with that function. And if you take time derivative of that charge, you can get the current. So current is given by minus omega times Q times sinus omega t plus phi. What do you see here? The current changes by time with that function, okay? So if you plot these two equations, you can get this one and this one. I will show you. So what we have here, what is this omega? Omega is given by 1 over LC power 1/2. This is angular frequency of oscillation in an LC circuit. So the frequency of this one, So now let's have a look. This is the charge as a function of time. When the time is 0, the Q is given by maximum Q and phi is 0, okay? Then as a function of time, it decreases, it goes to 0, and then it goes to negative maximum, and it goes to 0 again, and it goes to positive maximum again. So with that function, it changes. And this is the angular frequency of that oscillation. And let's have a look at the current. When the time is 0, remember the sign is 0. It is 0, okay? And it goes to maximum, it increases, and then it decreases to 0, and then it goes to negative maximum, and then it goes to 0 again with that sinus function, okay? And this is the angular frequency of that electrical oscillation in an LC circuit. So now let's finish with the energy in an LC circuit. So the total energy in the capacitor is given by Q square over 2C. This is the capacitance of the capacitor. This is the total charge, maximum charge of the capacitor, okay? This is the maximum energy. At the beginning, there is no connection between capacitor and inductor. So we fully charge the capacitor by using an EMF, and the energy of the capacitor is given by that expression. But here, for certain time, when we close the switch here, so some part of this total energy is shared by the capacitor and inductor, okay? So for certain time, we have current in the circuit. For this reason, we have that energy in the inductor, and then we have that energy in the capacitor. So when the Q is different from 0. And the energy within that system is conserved. Any question here? Now let me show you the analogy between electrical and mechanical oscillations. What was the mechanical oscillation? You remember mass spring system. Let me draw here. So let's consider there is a wall here, and then here we have a mass, and here we have a spring, okay, connected to the wall. And let's consider this is X is 0, okay? And if you stretch that spring in that direction, or if you compress the spring in that direction, there will be a simple harmonic motion from the maximum amplitude, okay? Between the maximum amplitudes, it will be like this. This mass will move like this. This is simple harmonic motion, okay? This is the behavior of this one, okay? Behavior of this one, behavior of the current, behavior of the charge, very similar to the oscillations in mass spring system. Even the equations are very similar. I will go into detail. Look at the equations for the mass spring system we have done in physics 1 in chapter I think, where is it, 14? Yes, chapter 14, simple harmonic motion. So look at this one. Kinetic energy is given by 1/2 mv squared when the mass is staying at the equilibrium at the beginning. Velocity is 0, and the potential energy is also 0 because it is staying at the equilibrium. X is 0. Remember the simple harmonic motion. And then when we stretch it or compress it, we have potential energy. We store potential energy in the system, in the spring. And when we release it, so this potential energy is converted to the kinetic energy, okay? And the total maximum energy is shared between potential energy and kinetic energy as a function of time in the simple harmonic motion, okay? This is the total maximum energy of the system, and this energy is shared between kinetic energy and potential energy as a function of time. So this is the velocity for certain position of the mass, and this is the angular frequency of the system, and this is the x as a function of time. So what do you see here? Magnetic energy in the inductor, look at the equation, 1/2 mvx squared, 1/2 li squared. And potential energy in the mass spring system, so electrical energy in the capacitor, 1/2 1/c q squared. So instead of 1/c, you can see k, and then instead of x square, you can see q square here. So the total energy shared between the magnetic energy and electrical energy here, kinetic energy and kinetic energy and potential energy. So again, the expressions for the current and velocity very similar. And what we have here, we have current, we have a velocity here, we have angular frequency of the electrical oscillation in LC circuit. Here we have angular frequency of the mass spring system. So we have this kind of analogy between electrical and mechanical oscillations. So just to remind you. So now let's continue with an oscillating circuit. So here we have a power supply, 300 volt DC power supply is used to charge a 25 microfarad capacitor. Here we have a capacitor, here we have an EMF, and here we have an inductor, and here we have a switch, here we have another switch. So this EMF is used to supply power to that capacitor. The capacitance of the capacitor is 25 microfarad, which is given, and the EMF of the DC power supply is given by 300 volt. And when it is disconnected from power supply and connected across a 10 milli Henry inductor. So we close that, we open that switch. First of all, we fully charge the capacitor by using the EMF, and then we open that switch and close this one. So now we have current in that circuit, okay? At the beginning, we have current in that circuit, and when we fully charge the capacitor, we have current in that circuit like this. So now what is the question? Find the frequency and period of oscillation of the circuit. We have learned that the current will oscillate in the system, okay? First of all, there will be direction like this, and then the direction like this, and like this. So there will be oscillation in the current and the charge in the circuit. So the question asks the frequency and period of that oscillation. The second question, find the capacitor charge here and the circuit current 1.2 millisecond after the inductor and capacitor are connected. So now let's have a look at the first question. The angular frequency is given by that expression, inductance is given, and capacitor is given. Put them here, then you can calculate angular frequency 2 times 10 to 3 radian per second. And another question is frequency and period. Frequency is given by that expression, depends on the angular frequency. You can find 320 hertz by using that information here. And the period is given by 1 over f, 1 over frequency, and then period is given by 3.1 millisecond. So now, what about the capacitor charge and current after 1.2 milliseconds? So capacitor charge is given by that expression. We have already calculated the initial charge times cosine omega t plus phi. The charge is maximum when the time is 0. We fully charge the capacitor. When the time is 0, we have the maximum charge, okay? And put t0 here when the time is 0. And when the time is 0, this small q is also equal to q, okay, maximum charge. And then this phi will be 0. So instead of q, instead of charge, I can use this expression, capacitance times EMF, okay? We have learned this one in the capacitors in the previous chapters. So capacitance is given, and EMF is also given. Put them here, then we can calculate maximum charge. So, but what was the question? What is the capacitor charge 1.2 millisecond after the inductor and capacitor are connected? So in order to calculate this, put the charge here, this one charge, the maximum charge here, and instead of cosine omega t, we have calculated omega here, angular frequency, put it there, and the time is 1.2 millisecond, which is given in the question. Put it there, then you can calculate the charge after 1.2 millisecond, which is given by minus 5.5 times 10 to minus 3 Coulomb. And what about the current? Current is given by that expression, okay? Minus omega q times sinus omega t plus phi, but we have seen that phi is 0, then you can skip it here. So just put everything into the current here, then you can calculate current is equal to minus 10 amp after 1.2 millisecond when they are connected to each other. Do we have any question here in that problem? Okay, then let me continue about the energy in an oscillating circuit. Here again, we have the same circuit, LC circuit. And question asks that find the magnetic and electrical energies when the time is 0 and at time is equal to 1.2 millisecond. So when the time is 0, there is no current in the system and all energy is stored in the capacitor. So the magnetic energy in the inductor is 0 because there is no current in the system when the time is 0. So magnetic energy is 0. So the energy stored in the capacitor is given by Q square over 2C. Q is given here. We have calculated Q. Okay, put it there. And capacitance of the capacitor is also given. Put it there. Then finally, we can calculate the charge stored in the capacitor is given by 1.1 joule. Okay. So at that time, we have a current in the circuit. For this reason, this initial energy in the capacitor is shared by capacitor and inductor with that relation. Okay, so magnetic energy can be calculated like this, but you need to calculate the current when the time is 1.2 millisecond. Actually, we have calculated current when the time is 1.2 millisecond, okay? Put that current here, then the magnetic energy after 1.2 millisecond is given by 0.5 joule. And the remaining energy is still in the capacitor and it is given by that expression. So what about the charge after 1.2 millisecond? Actually, we have calculated the charge after 1.2 millisecond, which is given by that expression. Put it there. Finally, we have electric energy stored in the capacitor is given by 0.6 joule. So what do you see here? At the beginning, when the time is 0, all the energy is stored here and given by 1.1 joule. But after this time, the energy is shared by the capacitor and inductor. And what about the total of that energy? The sum of that energy is 0.5, 0.6. It gives 1.1 joule, okay? So this condition is preserved, let's say. But we consider that there is no resistance in that system, so no energy is dissipated due to the resistance. And this is ideal case, let's say, but in reality it is not like this. So we will see that in reality we have resistors in the circuits, okay, and we have also resistance of the wires. So then this type of circuits, LC circuits, goes to LRC series circuits. So here we have this type of circuit here. We have EMF, we have one switch here, and then we have capacitor, we have inductor, we have resistor. And at the beginning, we use the switch position like this, and then we fully charge the capacitor, and then change the position of the switch. Then we have current like this in that circuit, okay? So if there is no resistor in the circuit, or if the resistance of the wires and the resistance of the inductor is zero, are zero, then there will be no energy dissipation in this circuit. So there will be oscillation like this, okay, if there is no resistance. But here we have a resistor, then some part of the energy will be dissipated within that resistor. So what about the result? So let's apply again Kirchhoff's loop rule for that circuit. We have resistor here, we have inductor and potential across the inductor, and here we have potential of the capacitor, and they are equal to zero according to the Kirchhoff's loop rule. So here we have I, instead of I, just use dq over dt, and then rearrange that equation. So finally we have this expression. What do you see here? We have one additional term here if you compare with the LC circuits. Let me go back. Look at this one. Here we have this term, and here we have Q, and here we have an additional term. Let me go back. Do you see in LC circuit? But in LRC circuit, we have an additional term, just this one. If you consider that there is no resistor and the resistance of the system is zero, then this term is zero, then this equation goes to LC circuit, okay? So this is the main difference between LC circuit and LRC circuit. So if you solve that equation, you can get expression for the Q. Again, charge on the capacitor, and the charge on the capacitor oscillates by time, okay? So if you take the time derivative of that charge, you can get the current, okay? It will be given by sinus function, and it is also oscillating, okay? Its direction changes. But what is the main difference between LC circuit and LRC circuit? So now we will see that. So in the LC circuits, the angular frequency is just given by that term, but in addition to that term in LRC circuits, we have this additional term due to the resistance. If the resistance is zero, then this term is zero, this term goes to 1, and the equation goes to LC circuit, or charge of the LC circuits, okay? So now let's have a look the behavior of charge as a function of time. This is the time, this is the charge. We know that the current will oscillate, it will its direction will change by time, okay? But what do you see here? In LC circuits without resistance, we have oscillation, but the magnitude of charge or amplitude was same, right, for each condition. But what do you see here? The charge decreases by time. I mean, the magnitude of the charge decreases by time, and the magnitude of the charge goes to 0 by time. So the capacitor after certain time will be fully discharged, okay? Because the energy is dissipated in the resistance of the resistor. If there is no resistance, or if there is no resistor in the circuit, then there will be no energy dissipation and it will behave like LC circuits, okay? So current and charge does not change, okay? So they are decreasing, they are increasing, but the maximum charge and maximum current does not change in the system. But in case of LRC circuits, maximum charge and maximum current in the circuit decrease as a function of time. So finally they go to 0. So this is the behavior of the LRC series circuit. This behavior is called as damped harmonic oscillation, okay? The previous one was harmonic oscillation like this, okay, with some certain angular frequency, but this is damped harmonic oscillation because it goes to 0. In Turkish, you can say sönümlü harmonik hareket, okay? Due to that behavior of the angular frequency of damped oscillations. So the practical applications of such circuit emerge when we include a sinusoidally varying source of EMF in the circuit. So they are very useful in applications in such circuits. So such a circuit is called an alternating current circuit. During the next week, we will go into detail of such circuits. So now let me play a little bit that equation. We have seen that the charge on the capacitor changes as a function of time with that behavior, and it goes to 0. This is called as underdamped circuit when the R is small. When the R is 0, we have normal simple harmonic motion. But if we have a R, then we have underdamped oscillation, okay? But let's consider that here we have R square. This R square is equal to 4 times L over C. Put this one here. Then this term will cancel this term. If I use this R square, 4L over C here instead of R square. So then omega prime angular frequency will be 0 if this cancels this one. What is the meaning of 0 angular frequency? 0 angular frequency means that there is no oscillation, okay? So this term will be 0 and there will be no oscillation by time, and the charge will decrease with that relation like this. If we have larger resistance like this is critical resistance, let's say, and then we have critically damped circuit we have in the circuit. And the charge does not oscillate anymore, okay? It just goes down with that relation. If you further increase the resistance of the system, so what will happen? So then this term will go to smaller values, and this term will go to smaller values, then charge again will decrease that behavior. So what do you see here, that charge decreases faster in this case than this case. Okay, and this, the last case, is called as overdamped circuit for very large resistance in the circuit. Do you have any question here? So in applications, usually this condition is used. Okay, this is my last transparency. Here we have what resistance R is required to give an LRC series circuit a frequency that is 1/2 the undamped frequency. So this is the question. This is the underdamped frequency for the LRC circuit, and this is the undamped frequency for the LC circuit. So this is for LRC circuit, and we know that for the LC circuit we have this behavior. So the question says that frequency that is 1/2 the undamped frequency, that expression. So we know that omega prime under damped frequency is given by that expression, and undamped frequency for the LC circuits is given by that expression. We have done it in the previous transparencies, and we have that condition 1/2 here. Okay, if you take the resistance from that equation, you can find it like this. Okay, so the resistance is asked within that question. Okay, let me summarize the difference between LC and LRC circuits. In LC circuits, we have capacitor and inductor here. Okay. Inductor. And in LRC circuits, we have one additional resistor here. So the behavior of Q, charge or current, is a function of time for this one is given by that one, okay? Like simple harmonic motion. But in case of this one, we have this type of behavior of the Q as a function of time. So what do you see here? That the amount of charge on the capacitor decreases by time. So this is the main difference. If there is no resistor in the system, we have simple harmonic motion, okay? There is no dissipation in the system, but whenever you put resistor, or if the wires and inductor has certain resistance, then the charge and also current in the system decreases as a function of time with the equations which we have calculated. Do you have any question? Okay, if not, then I will close this session. So the second midterm exam date is announced, okay? And you have less than 1 month. I strongly suggest you to repeat all the chapters which you will be responsible during the second midterm exam, and then try to solve the problems at the end of the chapters. So I'm repeating again that if you cannot solve some problems at the end of the chapters, please write me an email, send the questions and problem numbers, and then we can arrange a meeting to solve that questions. So take care of yourself. Bye-bye.